Welcome to the Math Show Skill Drills with Mr. DeClerico. If we want to solve logarithmic equations, we're going to need a game plan. Specifically, a game plan we know is going to work. The first step will be to isolate one logarithmic expression. This may require condensing. If you're not sure what condensing a logarithmic expression means, refer to my last video, which I've included in the description. Second, we're going to exponentiate. That means set both sides of my equation as exponents of a common base, strategically. My third step is to solve the new equation created by exponentiation. And finally, we'll need to check for some interesting critters called extraneous solutions. Turns out we can do steps 1 through 3 totally right and still sometimes get a solution that isn't. We'll learn how to deal with those later in the video. By the way, go birds. Let's solve a basic logarithmic equation. Log base 6 of x equals 2. As you can see, I already have an isolated logarithm, so step 1 is done. On to step 2, exponentiation. I have a base of 6 in my logarithm, so 6 is going to be the base I'll use for exponentiation. 6 to the log base 6 of x gets me x. So x equals 6 squared, which is 36. That's cool and all. But what if this yellow dish sponge appeared and told you to bring it around town? Well, what does that mean? Well, this is an interesting trick that I learned that makes exponentiation simple and perhaps even fun. Check it out. Here's the problem. Log base 6 of x equals 2. Follow this pattern. My solution will be 6 squared equals x. That's easy. X equals 36. Bring it around town. Here's another simple logarithmic equation to try. Feel free to pause the video and try to solve this one on your own, either with exponentiation or bring it around town. Okay, I'll assume we're ready to continue. I'm going to exponentiate with a base of 3, since my logarithm has a base of 3. That means x equals 3 to the 4th, which is 81. If we were going to bring it around town instead, here's my pattern. 3 to the 4 equals x. That means x equals 81. What's this sailing in? Looks like a caveat. Bring it around town is a neat little trick that can be used for quick exponentiation. However, if you see one of these signs in the problem, that means that you're solving a logarithmic inequality. And if you're doing that, I would not recommend using Bring It Around Town because there's an additional step that's very easy to forget. I don't want you getting mixed up, so pay attention to this caveat and don't use Bring It Around Town for a logarithmic inequality. Let's try a more interesting logarithmic equation. Log of x plus log of x minus 48 equals 2. Now, the way I often see students start a problem like this is they apply a base of 10, which is a good instinct because if you don't see the base of a logarithm, that means the base is 10. It's common log. But if you're paying attention, you'll notice that this first step totally ignores the first part of my 4-part game plan to solve logarithmic equations. I need to get down to one logarithm. Otherwise, it is very likely that I'll need to issue an order of operations alert, because an order of operations error is very likely in your future. Why is that? Well, that part on the left-hand side does not deal with the logarithms. Why is that the case? Well, an exponent is a group. It's kind of like a grouping symbol. I need to add these logarithms together before I apply them as an exponent of the 10. If I just put this 10 here and I say it'll take care of all the logs, that's doing order of operations incorrectly, and I will not get rid of all my logs. I'll just make a big mess. So though this is a redeemable first step, I'm just going to recommend you not go this route and follow my 4-step game plan. What's a good first step then? Well, check this out. We're going to use the product to sum law. Log of x plus log of x minus 48 equals log of x times quantity x minus 48. The sum of the logs is the log of the product. I've condensed my logarithmic expression on the left-hand side. Now I'm set for success. All right, now let's solve this logarithmic equation now, shall we? We know we need to condense the logarithmic expression on the left first. There it is. Now we're able to exponentiate. Step 2 is complete. And we get the desired result. No more logarithms. So now what I'll see students do is say, oh, well, I factored on the left-hand side. That's convenient. X equals 100 and x minus 48 equals 100. I'm almost there. Well, nope, that's a mistake. We need to use 0 product property, not 100 product property. Get that 100 over to the other side. Don't underestimate the potency of that mistake. That'll totally wreck your problem. Now we can factor, and we have a 0 on the right-hand side. We're ready to solve. X equals 50, and x equals, nope, not -2. -2 is an extraneous solution. That means it's not actually a solution, even though our algebra was correct. Well, why is that? Well, imagine if we substituted a -2 into this equation. You substitute it into that first x, and you immediately have a problem. Remember, logarithms can only receive positive inputs, so 0's not allowed, and -2 is definitely not allowed. So since we can't input -2, it can't be a solution. And here he comes, Mr. Platypus, with his questions. Why do we get extraneous answers if our algebra is correct? Is algebra broken? Oh, far from it. There's something we need to pay close attention to. We saw that we could use good math to get from this logarithmic equation on the left to a polynomial equation on the right. We mentioned that logs must have positive inputs. But polynomials can have any real input. The domain of a polynomial is all real numbers. So, since I converted to a polynomial from a logarithmic equation, I can solve this polynomial and get 2 answers that would both work for the polynomial, not necessarily for the logarithm. But the logarithmic equation is what we're actually trying to solve. So I would need to substitute both of those answers into the logarithmic equation to make sure they both work. And -2, though it works for the polynomial equation because it's a real number, does not work for the logarithmic equation because it's not a positive real number. Here's another logarithmic equation. Take a moment, pause the video, and see what you think the first step should be. All right, I'll assume we're ready to continue. My first step would be the first step of the game plan I outlined at the beginning of this video. We're going to need to isolate one logarithm on the left-hand side, which means we will need to condense. The difference of the logarithms is the log of the quotient. Then I can exponentiate with the base of 2, or just bring it around town. From there, it's a bit of algebra. And then I get that very messy answer that just so happens to be true. If you don't believe me, I checked my work. Feel free to pause the video if you want to pay close attention to the algebra or the check. All right, let's move on. Now here are some logarithmic equations for you to try. Feel free to pause the video and give each of them a go. All right, I'll assume we're ready to continue. The correct answer for the first one is x equals 8 over 7. Start by combining those logarithms on the left-hand side. The difference of logs is the log of the quotient. Then exponentiate, solve the equation that follows, and you're home free. Basically, the same process applies to the second equation, except that you're going to get an extraneous solution. Negative 1/2 does not work because log base 5 of x and log base 5 of 4x cannot receive negative 1/2 as an input. Positive 1/2, though, causes no issues. It's a legit solution. And that's all for today. And if you're feeling what Mr. Platypus is feeling, check out my website in the description. And as always, be sure to click subscribe, hit the like button, and all that good stuff.